Test. I guess good afternoon, everyone. As Paul mentioned, my name is Yan, and I guess before I start, can I just get a quick show of hands? How many of you have heard of serverless? Pretty much full room, great. How many of you have heard of chaos engineering? Okay, great. That's pretty good. So I work for a company called The Zone, and we've got offices in both London as well as Katowice. And as Paul mentioned, we are building the Netflix of sports, basically an affordable platform where you can watch all kind of sports live on your computer. And the reason my company allows me to take time off and come to here is because we are hiring. So we are hiring in the London office as well as in Katowice. So if you want to go come and check it out, feel free. But before I talk about chaos engineering, I want to just mention smallpox. You've had a lunch, so you're okay. So smallpox has been one of the most deadly diseases that we have ever encountered as a species, and it was killing people by hundreds of thousands a year until I guess 1798 when Edward Jenner developed the first vaccine, and 200 years later we eradicated smallpox globally, which is quite an achievement for human beings. And nowadays, we have 25 different vaccines for different infectious diseases. And in the UK, at least, by the time you're 14, you will have had 20 injections, 20 different vaccinations already. And the vaccination has become the most effective defense that we have against infectious diseases nowadays. And it works by injecting you with a small sample of the disease. So it gives your body a chance to react to and discover these diseases and start building resistance against them before you actually get into contact with the disease for real. And this has a lot of parallels with the practices that we use for chaos engineering, which is a discipline to use controlled experiments to help us learn about our system's behavior and start, behind the mic, and start building confidence and the resilience. And start building resilience. And start building a resilience against in our system against these failures and build confidence in its ability to survive in production over time. And we do this by injecting small doses of failures purposefully into the system, so that we identify failure modes we may not know about our systems have, so that it gives us time to build resilience against those failures before they actually happen in production. And it worries me a lot whenever I see posts with titles like that, because it puts a lot of emphasis on just breaking stuff. And as a reader, I might even conflate the action of breaking things with the payback, because the point of chaos engineering is not to hurt production. It's about learning. It's about identifying and finding out failure modes before they actually happen, so they give us a chance to build resistance against them. Imagine if medical professionals conflated the action of injecting with vaccination with a payback and thought, hey, the point of vaccination is to actually give you some disease. That would have ended up really badly for us, right? And if you go to principlesofchaos.org, you can find the principles of chaos engineering nicely documented, where we have 4 simple steps that we can follow to start planning and executing chaos experiments in practice. First, you start by defining your steady state. And if everything is on fire all the time, then unfortunately you don't have a steady state and you're not ready to start doing chaos experiments. And for the same reason that you wouldn't vaccinate someone if you know their immune system has been shot a bit, and injecting them with even small doses of disease will still do more harm than good. In the same way that when you don't have a steady state, everything's on fire all the time, by doing chaos experiments, you're just going to make things worse. But once you have to have that steady state, then you're in a position to start designing scenarios and hypothesizing how your system would behave under those scenarios. And if you're going to run experiments in production, and you should, you need to have a reasonable degree of confidence that your system would actually handle those failures before you start to run those experiments in production. By all means, you should run scenarios where you just have no idea how your system is going to behave, and they're great for learning, and they're great for identifying weaknesses very quickly, but maybe you shouldn't start doing them in production as first. Start them in a staging environment, something that's production-like, where you can have where there's a less stake at risk. So you give yourself a chance to learn about those failure modes in a safe environment where breaking things is not going to hurt production, and also give yourself a chance to learn how the motions of planning and executing experiments and learning from them. And then as you learn more about your system's resilience, then you start to build up confidence over time. then some of those experiments can start to graduate into production. Just as the goal of vaccination is not to actually catch a disease, the goal of chaos experiment is not to hurt your production environment either. And if you know something's going to break in production and you did it anyway, then it's just being irresponsible. For starters, you haven't even learned anything you didn't know before the experiment, and all you're doing is breaking production and hurting your users and making your users angry. And once we've identified the scenarios that we want to run, the experiments we want to carry out, now we comes to talk about how we're actually going to inject those failures. And the most popular tool, and this is the most well-known tool, is Netflix's Simian Army. And Netflix also published a free ebook you can download that discuss not just the technical side of things of doing injections, but also the social side of things. How do you communicate to teams? How do you plan those experiments? How do you do all the things around the experiment itself? Understanding after the experiment, how do you then find out those results and prove your hypothesis? And the Gremlin has also launched their own commercial offering, a tool for running chaos experiments, and they also have a lot of automation built into their platform as well. And once you've run your experiment, then you have to go through all your data to make sure that to try to prove or disprove your initial hypothesis. And once you've identified some weaknesses by looking through the metrics, then now it's time for you to put in those engineering effort to build those resilience into the system so that before those failures actually happens in production. And I will just keep iterating in this talk that chaos engineering is about running controlled experiments. It's not about hurting production. So how do you keep those experiments under control? For starters, you need to make sure that everything is well communicated. If you're going to run an experiment that's going to impact some other team system, make sure that everyone is aware of what you're doing, and then that they're okay and ready for it. There shouldn't be any surprises. I shouldn't come into the office and realize that all my metrics are red, alarms are firing off everywhere, and when I look into it, I found out that it's because you're running some experiment that's impacting my system. That just shouldn't happen at all, right? And then there's also a matter of timing of when you run those experiments. You should run them during office hours when people are at work so that they can deal with any unexpected fallout. There's always an element of risk when you run experiments, especially in production. So having people in the office and available to deal with any unexpected fallouts is very important. And if you've got any important dates coming up, like the launch of a new TV show or a big feature, then also by all means avoid those dates altogether. And perhaps most importantly, that the containment of the blast radius should be the front and center of your thinking, especially if you're planning to run experiments in production. Because again, the point is not to actually hurt production. So to do that, you want to do the smallest change possible that still allows you to detect whether or not your steady state has been interrupted. And then you should have a rollback plan in hand so that should anything happen, you should just stop the experiment as quick as you can and then roll back. And once you hear that a lot of big companies, the Netflix, the Uber, the Amazon, and Microsoft, talk about running experiments in production, and you should definitely do that as well, but that's probably not where you should be starting. Start again from in a staging environment, run experiments. There's an awful lot of things you can learn about your application's weaknesses just by running experiments in staging. Give yourself a chance to learn the motion of doing experiments before you try to go anywhere near production. Even the big companies like Netflix and Uber and Amazon, they didn't start these practices of chaos engineering in production either. Everything started in staging. Once you got enough confidence that the system is actually going to deal with the failures that you want to inject properly, then you start to think about, should I maybe run some of those experiments in production as well? And chaos engineering is not just about stress testing your infrastructure. As Ross Miles points out, that you can address all the different aspects of the socio-technical system that we do for software engineering nowadays. Ross can talk to you all about the social aspects of in terms of communicating upwards to the stakeholders about why you want to do chaos engineering. And one of the most important things I learned from him is that maybe don't call it chaos. Instead, call it what it is, which is continuous resilience testing. It's a lot easier to get buy-in from the stakeholders when you avoid the word chaos, which puts a lot of emphasis on breaking stuff. Trust me, when your stakeholders is not going to be happy to hear about, oh, what, you just want to break production? That's not what you're doing anyway, but the way you communicate it should also reflect that as well. For the rest of this talk, I'm going to focus on the technical side of things in terms of how do we then apply the practice of chaos engineering to your serverless architecture. So I mentioned the Simian army earlier. From that toolkit, you've got your latency monkey that can inject artificial delays into APIs to simulate what happens when some API you're talking to is slow. You've got Chaos Monkey that kills a random EC2 instance. You've got Gorilla that kills the entire AWS availability zone. And then you've got Chaos Con that just knocks out an entire region altogether. And there's also been several efforts to basically allow you to run Chaos Monkey inside a Lambda function. But so far, I haven't seen enough effort in the community to basically apply the same principles, but rather than running them from a Lambda function, but applying them against your serverless architecture running with AWS Lambda. Because a lot of things have changed with functional service, with serverless, you don't have access to the server that runs your code anymore, at least no server that you can access and you can kill. And chaos engineering is not about killing servers in the first place. That's the most commonly applied practice that we do in production because of the tools that's available and because of the paradigm that we've been using to develop and run software up to now. But it's about identifying weaknesses before they manifest in production in a system-wide aberrant behaviors. So we shouldn't confuse the principles, which is why we do something, with the actions that we do in order to apply those principles. So in one of my previous companies, I worked on the non-trivial serverless architecture, whereby I migrated a social network to run pretty much entirely on serverless. And in there, you can see a lot of Lambda functions, but also other serverless technologies like DynamoDB, Kinesis, and so on. And one of the things I learned is that there are just way more inherent chaos and complexity in a serverless architecture compared to something running on CC2 or on containers. You have much smaller unit of deployment and scaling, which is great for many benefits, for many reasons, but you also end up with a lot more of them. So now it becomes harder for you to harden around the boundary of those individual units of deployment and scaling because you just end up with so many more of them. And one of the things you also notice is that people that are building things with serverless technologies, we just don't want to run servers, we don't want to manage them, which means chances are you're going to see a lot of managed services being used in the mix as well. And of course, each of these services have got their own set of failure modes. Some of them are documented, but chances are most of them are not. And even if they are documented, we don't really have a way, we don't have the necessary access or control of those services to be able to verify those behaviors when something does go wrong. And then there's also the matter of configurations as well. Instead of configuring things on a per server or per container, now you are configuring everything down to the function level. And there's a lot more configuration, both in terms of application level, the permissions, timeouts, and so on. And there's just way more chance for you to misconfigure something or just forget to configure timeouts or whatever for one of these functions. And then there's everything the platform does for you, from scheduling a container to run in your code, to polling Kinesis, to retrying failed invocations, and so on. All of those things have got their own set of failure modes. And again, most of these failure modes are not obvious to us because chances are they're tied to implementation details and they're not documented. And even if they are documented, they can change without any notice from the platform. For example, if something happens and it prevents Lambda from being able to poll Kinesis and call your function with Kinesis event, we don't really have any meaningful alternative than to just wait it out and wait for Amazon to fix the problem. That said, there are still a lot of weaknesses in our own code, in how our code deals with our external dependencies that we can identify with experiments. For example, maybe we are missing a proper timeout handling when we talk to external APIs, or maybe we are missing some error handling, or we're missing some fallbacks when our downstream systems is unavailable. In terms of the sort of problems that I see in production, the most common problem I run into tend to be latency or performance related, and they can be symptomatic of a whole bunch of other things that are happening that's wrong. It could be Amazon having problem with their networking. It could be you're talking to a server that's overloaded, so the response time has spiked as a result, or it could be just simple garbage collection taking a long time. So how can we then apply, design experiments to identify these weaknesses? Again, you start with your steady state as to what metrics you want to monitor to define your steady state with. That kind of depends on what application you're building. Some common good candidates include 95 and 99 percentile latency numbers, error counts, or the percentage of requests that you were able to complete. And once you have your steady state, you define your steady state, you can now start to hypothesize and design scenarios about how your system should behave in those when you inject those failures. And there's a couple of things we need to understand about our serverless application as well. For example, if you're building an API with API Gateway and Lambda, keep in mind that API Gateway has got a 29-second timeout. That's a hard limit. So even though your Lambda function can run for up to 5 minutes, API Gateway will stop listening after 29 seconds. And then there's also the effect of a cold start. So if you're talking to another Lambda functions through API Gateway, and you know the other Lambda functions got a very short timeout because maybe you configured it yourself, the actual response time you can experience from the calling side can still be a lot longer because of the additional latency the API Gateway layer introduces, as well as the cold start as well. And if you're running writing a Lambda function that's with Java or Scala, it's not uncommon for you to see a cold start time between 3 to 5 seconds. And when you're talking about getting VPC access as well, that can add another few seconds to your cold start time. So that can add a lot of unpredictability to the response time that you expect to see when you're talking to another Lambda function via API Gateway. And when it comes to microservices, the rule of thumb is to use very short timeouts. And that your goal for the timeout strategy should be to allow HTTP requests and give them the best chance to succeed, but not so much so that you end up causing the calling function to timeout or error. So that's where I find that trying to pick a fixed value for timeout is quite tricky. When it's too short, you're not giving the HTTP request the best chance to succeed. But when it's too long, then you run the risk of allowing those slow responses to cause your calling function to timeout or error. And it gets much worse as you have to make multiple API calls in one API handler. And I've seen two common approaches to doing this. Both of them have got their own shortcomings. For example, you got a function you've configured to have a 6-second timeout, and you know that you're making 3 separate API calls. I've seen cases where you will say, okay, for each of the API call is going to have a timeout of 2 seconds. So they are you divide the invocation time equally. But if one of the calls takes slightly longer, even though you've got enough time to make all 3 calls, you still end up terminating the call, timing out the call early. So you're not giving the HTTP request the best chance to succeed. Equally, I've also seen cases whereby your function's got 6 seconds. So for every call you're making, you're giving it just a little bit less than 6 seconds. So every request has got a 5-second timeout. Individually, none of them take that long, but together, you still call the overall time you're spending to make those API calls still be long enough and cause your function to time out instead before you have a chance to perform any recovery steps. So what I would propose is that we should set the timeouts for those API calls dynamically based on the actual amount of time that we have left in the function invocation. Fortunately, with Lambda, you can do this rather easily because when your function is invoked, you have a context which you can query to get how much time is left in the current invocation. And we can use that to set a timeout for all the API calls that we are making, minus a little bit of time that we reserve to perform recovery steps should any of those cause the timeouts. So in this case, even though the second request takes longer, but it's okay, we've got enough time left in the invocation, so we let it proceed. But if one of the request times takes longer to complete than the amount of time we have available, then we time it out. We still have some time left so that we can perform a number of recovery steps, which could be as simple as logging the timeout incident with as much context as possible, including what was it that you're trying to call, what was the timeout value, any correlation IDs that you've collected so far, as well as maybe the request object as well. And you may also want to record that as a custom metric so you can put that onto a dashboard. And also in cases where you can use the fallback value, and that's the pattern that Netflix has baked into the Historics library pretty extensively. For example, you're making a read to DynamoDB. If that times out for whatever reason, or it errors for whatever reason, maybe you can check, hey, have I made a similar query in the past for this user? And if I do I have a cache value that I can send back as a stale value instead, which is better than nothing? Or failing that, maybe I can return some default value instead. And that's exactly what happens when you go to the Netflix homepage, when they try to load your profile so that they can load those recommended watches. Yes, I was watching Benji. um, so whereby if they try to talk to their profiles, the profile service, if there are errors, then they try to return back a stale value that they've cached on the service for you. And failing that, they return the default set of tiles that they return for any new user that's joined the platform. And that, I think, is the perfect fit in terms of trade-off for this particular use case. But maybe not so much when someone tried to check the balance. Maybe at that point you don't want to return a stale value, an old value, or a default value of 0, which is going to freak someone out. So even though for many cases, sacrificing precision for availability is the right trade-off, you do have to keep in mind what is the right user experience that you want to give to your users. And that brings us to the kind of the exciting part of actually injecting failures into a system. And I think the first question I'll ask is, where should we do that? So imagine you've got a setup where you've got two edge services that the client application talks to directly, and both of them talk to some internal API. All of those runs on Lambda using API Gateway and runs on Serverless using API Gateway and Lambda. And I suppose the hypothesis is that all of our edge services are handling timeouts correctly, and then they will degrade gracefully when those requests fails, so that we prevent any cascade failures in this case. And as an experiment, I can inject latency into the HTTP client that my Lambda function uses to talk to the internal APIs. And then we will validate, in this case, I can validate that my functions have got a correct handling for timeout cases. And if timeout happens, it will handle them gracefully as best as it possibly can. And we should do the same thing when it comes to talking to third-party services that we don't control, maybe such as Amazon's DynamoDB, for example. And we can apply the same technique to inject latency into the AWS SDK that we use to talk to these AWS services. And in terms of the blast radius, remember, we have to make sure that the blast radius is contained as much as possible. For this particular experiment, it's relatively small. It's going to impact that particular function for sure, but also potentially the client is talking to the service. So if we identify weaknesses, so we did break that function. So in terms of instead of returning, I guess, a fallback value or some default value, we will error instead. Then that's going to impact that particular API call. But in terms of blast radius, it's still relatively small. There's no chance for you to cause a cascade failure into the entire system because you're only injecting failures into the edge of your architecture. Now, suppose if you want to broaden our hypothesis and to make sure that all of these edge services that talk to some internal API is handling timeouts correctly and is degrading gracefully when errors happen, then one of the things we could do is injecting latency into the internal API directly, so that this is the same as if you want to inject latency to all the HTTP clients for all the edge services that are talking to this internal API and validate them all at once. But in terms of blast radius, of course, this is where you can cause cascade failures if you're not careful. So in terms of blast radius, it's quite big and it's quite risky. And remember, we don't want to break production. So whilst this type of exploratory experiment is quite useful for weeding out weaknesses very quickly, they can also be quite dangerous as well, quite risky. So you should best to start doing this type of exploratory experiments outside of the production environment. And one of the things that I have kind of learned over the years and sort of one of the mistakes I've made over the years as well, is that we don't tend to prime our developers to think about failures early. What I mean by that is you start a new project, you're developing, everything's fine, you're developing against a dev environment where there's a minimal amount of load, so you never run into any problems in development. That's ready to load. There's no spikes in CPU, there's no spikes in traffic, so everything is hunky-dory. You see nice and fast response time all the time. There's no error whatsoever. And then production happens, where all kinds of things are going to happen. You don't control users, they all come in all at once. Why would they do that, right? But no, they cause all these spikes in traffic, things get slow, server gets overloaded, and the response time becomes longer and longer, errors start to happen. So, and we, as developers, we're not primed, we're not programmed ourselves to think about these errors early. So chances are our system is not going to be resilient against those kind of conditions that they're going to find themselves in production. And priming is a technique in psychology whereby you subtly influence the way someone thinks and behaves by repeatedly exposing them to a certain set or a certain type of stimulus so that over time, it becomes exposed to them constantly, so that they constantly thinking about that in the back of their head. And that's exactly what Facebook does with their 2G Tuesday practice, whereby on Tuesdays they dial down the internal office Wi-Fi speed to 2G, so that it simulates the kind of speed you're going to experience when you're talking about a developing country like Southeast Asia. And because Facebook wants to move into those markets, and they need their developers to constantly think about the sort of experience that people is going to have when they access the app in, say, a 2G environment. So the only way to make sure that everyone is constantly thinking about that is to make them experience what is it like to use Facebook when you only have a 2G connection. And again, this type of pretty risky experiments that can have a large impact can also be quite effective in making your dev environment better resemble the kind of condition you may find yourself in production that you should realistically expect your application to survive in production. For example, you may inject a constantly, you may say 3% of all of your cores is going to be slow by injecting some latency for 3% of the requests, or maybe say 3% of the requests will fail with 500, so that constantly, you're just feeding your developer to think about, you're exposing your developers to failure modes that they may not otherwise see in the dev environment, but they'll definitely see in production. And of course, the client app is also an important part of the whole system, and they are the last guard in terms of making sure that our users are given a good experience when failures happen. So you also need to test them for resilience as well. And to test weaknesses in the client application, you can also inject latency into the edge services, the function directly, so that you can validate that those client applications are handling timeouts properly. And again, because you're only touching the edge services in terms of the blast radius, is fairly self-contained. And when I first started doing chaos experiments a few years ago, when I was working for a games company, I was making an MMORPG game, and one of the first things we found was that as soon as I enable, say, 1% of the requests are having a slow response or have some error in the staging environment, we identify a number of critical weaknesses in the client app, whereby you have this hard-coded assumption that certain API calls will never take more than 3 seconds, and if they ever did, then the whole thing just freezes. There's no error, there's no pop-up, nothing. The whole app just freezes, like nothing is happening. And as well as we also found the missing error handling, missing retries, a whole number of other critical problems with the client app. And also, you don't have to inject latency into the edge services in order to test the client either. You can also apply the same technique that we showed earlier and inject latency directly into the HTTP client that your client application uses to communicate with your backend systems. And whilst the experiment is running, you're probably going to have your eyes glued onto the monitor on your dashboards, making sure everything's running okay. And as soon as the key performance metrics start to get impacted, stop the whole experiment altogether. And once the experiment is finished, go through all your other metrics and look for evidence that your steady state was impacted. So how do we actually then introduce inject latencies into the system? If you're talking about static languages like C# or Java, then you may want to use a static weaver like AspectJ or PostSharp, or maybe a dynamic proxies. And this is an approach that I talked about quite a few years back on how to do that, certainly with C#. As for dynamic languages like Node.js, for example, which is something that I've been working very closely with nowadays, you can also craft your own wrapper library for your HTTP client, for example. And that's why I wrote my own HTTP client that wraps around the super agent library, which just have a very simple method for injecting latency based on some configuration to say whether or not we should do it, and also how often we should do it as well. And then to actually introduce some delay, just use the blueburst delay function. Pretty simple, straightforward. And to make an actual HTTP request, there's just one single request method, which again takes in some configuration from the option that's been passed in, and then inject the latency, and the configuration themselves are stored in SSM parameter store, which is a service that Amazon announced in 2016 and is part of the EC2 Systems Manager set of tools, and you can find it in the bottom left-hand corner of your EC2 console. And for testing purposes, in this case, I'm saying, okay, 50%, because I want to see the latency actually being injected, so I'm saying 50% of the request is going to have latency being injected between 100 milliseconds to 5 seconds. And I can also hook it up with Amazon's X-ray, so I can see the traces for the invocations. In this case, no invocation was no latency was injected, so the HTTP request finished in 60 milliseconds, which is pretty good. And in the case, I can find that 3.4 seconds was injected as the latency. And then when I see a slow response and I'm trying to figure out why there is, at least I've got a trace to tell me that okay, right, it's because of the latency that I'm injecting. So that's all well and good for HTTP client that has essentially just one method. What about for the AWS SDK? You can't quite feasibly manually write a client library for every single service that you're consuming. It's just not effective. So what you could do instead is apply a similar approach to Bluebird's promisify all factory function. And in this case, I've just got a pretty named injectable all method that takes a client object for AWS SDK that's already been promisified, and I override the async method to take in a config object like the one that we saw earlier. And in this case, when I run it, I can see in the logs when the additional latency has been injected into the AWS SDK's communication with the Amazon services as a result. All that code is available in the GitHub, so feel free to go and try it out. And we don't have to stop there as well for our experiments. We don't have to just say, okay, inject latency or not. We can also inject any kind of any type of errors that we want to test as part of our experiments. I think the key message I want to take away from this talk is that ultimately failures are inevitable, and the only way for us to truly know that our system's resilience against those failures is to put them to the test. Of course, we don't want to break production, so those experiments have to be under control. And through these experiments, we can learn about our system's weaknesses before they manifest in production, and then that gives us a time to then go and improve the system and make it more resilient over time. Unless, of course, you jump the gun and you decide to run a risky experiment in production and break it, then your stakeholder is not going to let you go anywhere near production to run those experiments ever again, so don't do that ever. And with serverless technologies like AWS Lambda, there are a lot more inherent chaos and complexity in the system. And if anything, there's more need for us to identify those weaknesses early so that we can start to build resilience and defense against them. And we do that by applying the principles of chaos engineering and vaccinating our service architecture against failures. So with that, my name is Yan, and just to say again, we are hiring in Katowice and London, and thank you very much for listening. I think we've got 7 minutes for questions. If anyone, okay, a question there. Yep. Mm-hmm. That the system under test, that the outcome of the system under test is identical to what we expect from the system in a steady state? Or if it is not identical, is this actually what we expect? Because now we have a bunch of blocks that this function has timed out, but how do we find out that, for example, the database didn't got into corruption state? Because how do we make sure that actually the system was vaccinated? Yeah, so the question is, how do you actually make sure the system is vaccinated when you're injecting failures, right? Okay, so well, that's where you have defined your steady state in terms of metrics. So, for example, if I say my steady state is that I should expect, say, 0.1% of errors, and when I inject latency, with the assumption that I know my system should behave such that it would handle those timeouts gracefully, so that we don't end up with errors. Instead, I'll return some cache value or some default value instead. So the steady state shouldn't be impacted in this case by the failures I'm injecting. Or for example, if I'm instead of latency, I'm saying, okay, 1% or 3% of the cores is going to have return 500 instead from the internal service, so that the edge services, they should be handling those 500 errors properly, gracefully, so it doesn't get passed up to the client. Again, that means from the client-facing, in terms of metrics, I should still have to see the same steady state of 0.1% error rate rather than it now going to 3% or 1% or whatever. So that's where you compare before and after. One of the things you might have to do is to well, you potentially can do this with metrics that where you can have different dimensions. So you can have metrics for everything else that where requests that are not under test, and metrics for requests that are under test, so that you can easily identify the differences. But even without that, you can still inject inject errors and failures to enough number of requests that bumps up the error rate enough. If you're only doing, say, 1 out of 1,000 requests, maybe you're not, even if you do have a failure, you're not able to see the changes in the steady state. But that's why you do the smallest amount possible, given how you're monitoring things, to make sure that when there is a weakness, you can see the change in your steady state. Does that answer your question? Okay. I'm going to be at the speakers table later anyway, so come we can talk about it some more. I think there's a question there. So the question is, what do you recommend in terms of how often, how frequently you run those experiments? And I think a lot of that depends on tooling, because if you're running them manually, then it means that requires a lot of effort. People spending time looking at things and responding to it. So that's where Netflix created this tool called CHAP, which is their automation process for running those experiments. So ideally, in the ideal world where you've got automation set up and all of that, then you should run it as part of your deployment pipeline, where there's some stage where you are testing for failures, you're testing for resilience, in the same way that as for Netflix, for example, when they kind of do this with the Canary deployment. So with Canary, you are kind of testing in production, but with say 1% of requests or 3% of requests, and you're monitoring at the same time before the whole chain was rolled out. But at the same time, you can also just include it as part of your pipeline earlier. One of the things that I wanted to do in my current job is that you should have like a performance load testing environment, whereby as part of your pipeline, before it gets to say staging or the production, there's a separate stage where every release candidate goes through that stage and is load tested, and maybe they should have something similar where every release candidate will go through another stage where it's tested for resilience as well. But again, that requires a lot of tooling or a lot of investment, and hopefully, I haven't checked out the Gremlin's tool itself, but hopefully with tools like that, it starts to become more of a service that you can just use to start to automate them for you. The difficulty of course, is being able to identify when you should quickly stop as well. So a lot of that comes with tooling, but that's something that you have to kind of work it out yourself. Ideally, as often as you possibly can with every release candidate, but that's the dream. Any more questions? Okay. Well, if no questions, I'm going to be at the speakers table, so come and grab me when you have time. Cool. Thank you.